Right, good morning everyone. Today we're going to look at phase difference. And basically we're going to do one thing. We're going to describe the difference between two oscillators. In this diagram, you have lots of oscillators. And this phase difference is creating a really interesting effect. It's a phase difference that's continuously changing. Now, you might not know what that means because I haven't explained it, but hopefully it will make sense by the end of this video. Before we get started, we need to go back to some basics. And that's the motion of an oscillator. Now, I've already mentioned that it does move according to cosine and sine functions. Now, it's no coincidence that those are functions that describe circular motion. And in fact, this is something we will definitely look at in high level, in more detail. But for now, I want you to consider the displacement of something that's moving in a circle, particularly just in the y direction. If I was to plot what was happening on the y-axis, the displacement purely on the y-axis, let me catch up with it, then basically you will see that that is giving us our oscillatory motion here. So this oscillator, this trace, this graph, is actually a reflection of that motion in a circle in the y direction. It's not something you need to understand to a high level, but just basically this should allow you to see why we can use circles and the way we describe circles as a way to represent the way an oscillator is moving. Now, one way to describe motion in a circle is to use radians. Now, radians are just a fraction of a circle. If you were to take the radius, which is this distance here, and measure it along the circumference, this is what we call an arc, right? So if this distance is the same as this distance, right, then that piece of circle is equivalent to a radian, right? So a radian is like, the best thing to think about it is like if you had a huge cake, right? And if you were to measure the radius and the radius here, and then it would basically draw out a very reasonably sized piece of that cake. Maybe that's something you can do next time you go to a birthday party. Give me a radian sized piece of cake. It won't make it very popular, but it will demonstrate that you understand this concept. So that's what a radian is. And we can express pieces of a circle using this concept, this radian. And once you know that you can describe an entire circle as 2 pi radians, right? Because if a whole set, well, I won't prove this because this is something you can do in maths, but basically what you need to know for phase difference is that if 360 degrees, an entire circle, is equivalent to 2 pi, then you can now find any fraction of a circle. So for example, 180 degrees, which is over here, 180 degrees is half a circle, right? So if 2 pi is 360, 2 pi times a half equals pi. And that's what 180 is equal to. We can continue with 90 degrees. If 90 degrees is a quarter of a circle, right, then 2 pi represents 360 times a quarter equals pi over 2. So 90 degrees is pi over 2 of a circle. Let's have a look at these. What I'd like you to do is actually try it yourself. If 360 is 2 pi, what does 45 degrees and 22.5 degrees do? If you totally get this, you can just go on to the next bit and ignore my next explanation. If you want to test yourself, stop the video, try it, and listen to my explanation if you don't get it correct. So the two answers you should have achieved, what you should have gotten was pi over 4 for 45 degrees and pi over 8 for 22.5. And how did I do that? Well, first, try and find what fraction of an entire circle 45 degrees is. So if an entire circle is 360, then 45 would be 1/8 of a circle, because it's 360 divided by 45. So 360 degrees equals 2 pi. What's 1/8 of 2 pi? Then 45 degrees in radians would be 2 pi divided by 8, which gives you pi over 4. Similarly with 22.5. What fraction of 360 is 22.5? If 360 divided by 22.5 now gives you 16, then 2 pi of a circle divided by 16 equals pi over 8. I hope you didn't listen to that if you already understood it, and I hope if you didn't get it, you get it now. So now you should be able to describe sections of a circle, pieces of a circle, using radians. Now, what has that got to do with waves? Well, you're going to apply that same idea to a wave, and a wavelength in particular. We can describe an entire wavelength. Okay, so this would be one entire wavelength. We can describe sections of this wave in radians. If 360 is 2 pi, then one entire wavelength, which would be equivalent of moving round an entire circle back to the same place, that would be equivalent to 2 pi. Half a wavelength from here to here is half a circle, which is equivalent to pi radians, because 360 divided by 2, which is half, or times a half, which is half a circle, gives you a pi. And then whatever fraction you're working with, whatever fraction of this wavelength you're using, would be equivalent to a certain fraction of 2 pi. About it like a equation. If you can work out the fraction of the circle, right, which is the length of the segment you're interested in, divided by the entire wavelength, that will give you a fraction. So for example, this distance divided by this distance, which is a half, times 2 pi will give you the fraction of the circle. If you have a tiny distance, just say from there to there, you would measure that distance, and then you would measure the whole wavelength. That would give you a fraction. You multiply that by 2 pi to give you your fraction of a circle. Now we're going to introduce the idea of phase difference. What exactly do we mean by phase difference? Well, for that, we need two oscillators, because phase difference is the difference in kind of journey or difference in position over time between two oscillators. And this is a great demonstration or simulation, on Cognity. First, we're going to start with no phase difference. So these two oscillators are in phase. There is no difference in the way that they're moving. So we say that their phase difference is equal to 0. They're doing the same thing at the same time. And when we plot both graphs, their position is the same. That's number 1, and that's number 2. Now we're going to look at a phase difference of pi. That's the easiest one to think about. Look at the way that they're moving. When one is reaching its bottom displacement, the other one is reaching the maximum in the positive. So it looks like they're reflecting each other. Let's have a look at their graphs. Number 1 is oscillating, and number 2 is doing exactly the same thing, but as a reflection of it. Now these are out of phase now. So let's have a look at that graph to try and figure out how we measure that phase difference. What is the difference in their path? Well, as you can see, when the green one is at 0 displacement, the blue one is at 0 displacement too, but it's coming in from a different direction. We're interested in the difference in path. What is the distance between this blue one that's coming up and the green one when it does exactly the same thing? So that would be here. The green one is now coming up and doing exactly the same thing. So we need to look at this distance. What is the fraction of a whole circle that this distance represents? So what is the ratio of this against all of that, the entire wavelength? Now you should be able to see that this distance is equivalent to half a whole wavelength, right? And that's why the phase difference is pi, because if a whole circle is 2 pi, half, which is the ratio of this over this, times 2 pi would give you pi. Let's have a look at some other ones. Let's get crazy. Let's do pi over 2, which is equivalent to 90 degrees. And you can see the way they're moving now. If we look at our displacement, that's what your first graph is doing. And basically, the other one is lagging. So we now need to consider this distance. This distance over the entire wavelength would give us a ratio which is going to be equivalent to a quarter, right? And you can see that it's a quarter of a circle there, etc. I do recommend that you have a play with this on Cognitive when I set this as a reading, if you haven't already. Right, so just to sum up, phase difference equals 2 pi times path difference over lambda, which is the wavelength. Okay, that probably sounds very different to what we've just done. Basically what this is your 2 pi times the ratio of the distance between the oscillators when they're in the same position. So this, the fancy word for this distance, is path difference. Although we haven't covered path difference yet, and we won't until much later. But this distance here, divided by the whole wavelength as a ratio, multiplied by 2 pi. And you can't go wrong with that. These two yourself, right? The first one's very straightforward, and you can simply just work out this distance either by having a look at it and working out the ratio, or you can get a ruler out. This one here, I would like you to get a ruler out and measure it. You can make the screen a little bit bigger and measure the distance. So find the path difference divided by the entire wavelength, right? So the distance between there and there divided by the entire wavelength. Stop the video, have a go, see what you get. And there you go. There's your answers. You should have seen that this is a quarter of an entire circle. That distance there is a quarter, which would be a quarter times 2 pi, which gives you pi over 2, 90 degrees. Well done if you got that right. Here, you should have worked out that this over that, from there to there, measure that distance, divide this distance by that distance, and you should have gotten something like 0.16 pi approximately. This is equivalent to 30 degrees, so you should get approximately a sixth, right? So anyway, I hope you did okay with that. If you didn't get these two, it's really important that you send me a message today, so I can give you further explanation and some more practice, okay, for tomorrow, because tomorrow we're going to go over some review stuff. Okay, so thank you very much and have a great day.